In section 8.1, we turn our attention to right triangles, and in particular, how to use trig functions to solve problems with right triangles. Precalculus Online starts now. Welcome to Chapter 8, and in this chapter, we turn our attention away from the unit circle and we start doing triangles just sort of out in the open, not necessarily connected to the rectangular grid. And so we need to sort of talk about how we're going to define the trig functions now. They're still equivalent to the unit circle definition, but we give them some new names and things. I think you'll be familiar with a lot of this material today. So let's draw a triangle. Just draw a right triangle here. And let's label this angle theta. And with this position of theta, we give new names to the legs and well, we still have the hypotenuse of the triangle, but the new names we have are based on the position of the angle. So we have the hypotenuse is across from the right angle, and then the leg of the triangle that is across the triangle here we call opposite, because it is opposite of the angle. And then the leg that is next to the angle theta is called adjacent, because adjacent means next to. And these names change depending on where the angle that we're talking about is. So if we had talked about the other angle, then the names would change slightly. So let's go ahead and define the six trig functions now. The sine of theta is the opposite over the hypotenuse. The cosine of theta is the adjacent over the hypotenuse. The tangent of theta is equal to the opposite over the adjacent. And there's a mnemonic that you can use to remember this, and it is so, ka, to, and SOHCAHTOA stands for sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. We can define the other three trig functions in these terms as well, and they are cosecant of theta is equal to the hypotenuse over the opposite. The secant of theta is equal to the hypotenuse over the adjacent, and the cotangent of theta is equal to the adjacent over the opposite. Usually what I do is I just focus on the first three and then take reciprocals to find the other three. Let's look at example 1. Find the value of the six trigonometric functions of the angle theta. So we have theta, we have a right triangle, and we're missing one of the legs here. Let me call it x. And because we have a right triangle, we can use the Pythagorean Theorem. So x squared plus 4 squared is equal to 5 squared. And this is our favorite one. We get x squared plus 16 is equal to 25. So x squared is equal to 9, and x is equal to 3. Because we're dealing with triangles just out in the open, there is no positive or negative orientation. All the legs in this case will be positive. So x is equal to 3. So the sine of theta is equal to the opposite over the hypotenuse. The opposite side to theta is the 4. So it's 4 over 5. The cosine of theta is the adjacent. So that would be 3 over the hypotenuse of 5. The tangent of theta is the opposite, which is 4, over the adjacent, which is 3. And now for the others, let's just take some reciprocals here. So the cosecant of theta is 5 over 4. the secant of theta is 5 over 3, and the cotangent of theta is equal to 3 over 4. Next up is the complementary angle theorem. First, let's recall what the word complementary means. Complementary means that it adds up to 90 degrees, and would be pi over 2 if you're doing this in radians, but usually we focus on degrees in this chapter. We have a triangle, ABC, and it is customary to label the sides of the triangle using lowercase letters that are opposite the vertex of the triangle that is represented by the capital letter. So capital A is a vertex that is opposite from side little a. Capital B is a vertex angle that is opposite little b. And capital C is the right angle, so the hypotenuse is little c. Now let's explore some of this here by looking at the sine of angle A. The sine of angle A would be the opposite side to A, which is little a, over the hypotenuse, which is little c. But if I turn that around and I think about A over C in terms of angle B, A and B are and angle B are adjacent. So that means the A is adjacent to B, which makes this the cosine relationship. But it's the cosine not of angle A, but of angle B. So the A is adjacent to angle B. And if I look at tangent of A is the opposite over the adjacent. That would be A over B. But that turns out to be the same thing as the cotangent of B, because cotangent of B is adjacent over opposite, but it's a different angle. Now let's look at secant of A. Secant of A is C over B, because secant is hypotenuse over adjacent, and B is adjacent to angle A. But that is the same as the cosecant of angle B, because B would be opposite angle B, and you would have hypotenuse over opposite if you're dealing with angle B. Well, the key here is to notice these relationships. You have the angle A, and then it's related in the same value to a different trig function, but of angle B. And the question is, what is the relationship between each of these trig functions in each of these equations? The relationship is that they are cofunctions. You have sine and cosine. You have tangent and cotangent. You have secant and cosecant. And so the complementary angle theorem says that cofunctions of complementary angles are equal. Cofunctions of complementary angles are equal. In fact, because of this relationship, complementary, right, means it added up to 90. The CO in complementary is where we get the term cofunctions. The CO in cofunctions is really just sort of short for complementary. In fact, if you think about where these names came from, what is the cofunction of the sine function? Well, they just shortened that to cosine. And that's where these other names came from. So we had sine, tangent, and secant, and then we ended up with cosine as the complementary co-function of sine, cosine, cotangent, and cosecant as well. So that's where all these co's come from. The co actually stands for complementary, and it's the complementary angle theorem is the impetus for all that. Let's look at some examples. Example number 2. The sine of 80 degrees is equal to the cosine of what angle? Well, just using the complementary angle theorem, the sine of an angle is equal to the cosine of the complement angle. So if I take 90 degrees minus 80 degrees, I get 10 degrees. So the sine of 80 degrees is equal to the cosine of 10 degrees, among other answers, but this is the exhibition of the complementary angle theorem. Example 3, the cotangent of 3 pi over 16 is equal to the tangent of what angle? So cotangent and tangent are cofunctions. So the complementary angle here, they would have to add up to pi over 2. So let me just take 3 pi over 16 away from pi over 2. I need a common denominator. So 8 pi over 16 minus 3 pi over 16 is 5 pi over 16. So the cotangent of 3 pi over 16 is equal to the tangent of 5 pi over 16. Example 4, solve the triangle. In this book, whenever we go with solve the triangle, that just means find all sides and angles. In particular, you just need to find everything that you don't already have. That's what solve the triangle means. So we're given that little a is 5. Now remember that little a is the side across from the angle A. And little b is 2. That's the angle across from angle B. And we have a right triangle denoted by the perpendicular mark in angle C. So we still need to find little c and the angles. So let's go with the Pythagorean Theorem. It says the hypotenuse squared, c squared, is equal to 2 squared plus 5 squared. C squared is equal to 4 plus 25. So c squared is equal to 29, and c is equal to root 29. And we'll go ahead and get a decimal on this one. We get 5.39. Next, let's go ahead and find angle A. It's better to use information that you were given with from the start to find this information. So I'm going to go ahead and do tangent of A, because A is opposite the 5 and adjacent to the 2, and those were the 2 pieces of information that I started with. So this will give me the most accurate answer going forward. So the tangent of A is the opposite, which is 5, over the adjacent 2. And then to solve for A, we just take the arctangent of of 5 halves. And that gives us 68.20 degrees. And then we need to find angle B. Well, angle B is the complement angle, because the 2 acute angles in a right triangle add up to be 90. So they are complementary. And so B is 90 degrees minus A, which is 21.80 degrees. Go ahead and round everything to 2 decimals on this, unless you need more decimals. In this section, let's talk about angle of elevation and depression. So let's suppose that we have a guy on a cliff. I draw these just like the cartoons. There it is. So here's a guy on a cliff. And he sees a helicopter over here. Then the angle to the helicopter with respect to the horizontal is called the angle of elevation. And then let's suppose that the same guy sees his friend down below by a river. Then the angle that he sees her with respect to the horizontal, call this an alpha maybe, this is called the angle of depression. So the angles of elevation and depression are always relative to looking straight across the horizontal, and these lines that they look through are sometimes called the line of sight. Let's look at example 5. Bob is on the balcony of his building, a height of 50 feet. He looks up through an angle of elevation of 18 degrees to see Kat on her balcony. The distance between the buildings is 130 feet. How high is Kat's balcony? So we just sort of draw a little sketch here. Draw Bob's building here, and he's on the balcony. Here's Bob. Bob's happy. And then here is Kat's building. And her balcony is a little bit higher because there's an angle of elevation. So we'll just draw hers here, maybe. Something like this. Okay, that's not as good. All right. Then we need to create the angle of elevation. So from where Bob is looking straight over, that's the horizontal. And then he looks up to see Kat on her balcony at an angle of elevation of 18 degrees. And we want to determine how high up her balcony is. Well, we have a couple of things. We know that he's 50 feet up, so we'll use that later. And we know that it's 130 feet across from building to building. Well, what we've done is created a right triangle right here. Mark that as a right triangle there. And we can use these opposite, adjacent, and hypotenuse relationships to figure out this height here, which I will call x. So according to the triangle, we have 18 degrees. What is the relationship from 18 degrees to the side we've labeled as x? That is the opposite. And what is the relationship between the 18 degrees and the 130 feet? That is adjacent. Which trigonometric functions is suggested by using opposite over adjacent? That is the tangent function. So we're going to have the tangent of 18 degrees is equal to the opposite, which is x, over adjacent, 130 degrees, 130 feet. Multiply both sides by 130, so we get x is equal to 130 times the tangent of 18 degrees. And so x is equal to 42.24 feet. Now what that represents is just the additional height from Bob's balcony looking up to Kat's balcony. And so to find her actual height, actually how high is her balcony, we need to go back and add Bob's balcony height, which was 50 feet, and we get 92.24 feet. Finally, we want to look at bearings and headings. A bearing is a direction. It's a direction in the form of, and it has three parts. You start with either a north or a south direction, then you give it the angle, and then you tell it it's either east or west. But it's always north, south first, then the angle, then the east and the west. The theta is an acute angle, so it's between 0 and 90. And everything is relative. The angle is relative to the north and south direction. So this is sort of the standard that everything is based off of. And by that, let me show you what I mean. Suppose we have this as sort of a coordinate grid system. And this is north, east, west, and south. And we want to talk about a bearing that is north 70 degrees east. So that means we start in the north and we go an angle that is 70 degrees toward the east, which is about right there. So we started north, and then we went 70 degrees. Now the question is, which way do we go? Do we go to the left or to the right? East is to the right on our grid, so we go 70 degrees toward the right. Now notice that you might be inclined to say, well, it's easier to mark this as 20 degrees because it's closer to the east direction. But they don't do that. They always do north-south, then the angle, and then which way did you go, east or west? So there's north 70 east. Let me go ahead and do south 42 degrees east. So we start south, open up about 42 degrees, about right there, toward the east. And one more, how about north 15 degrees west? So we start north, go out 15 degrees, very little, and to the west is to the left. So this angle would be 15 degrees. So they use this when talking about navigation, ships, planes. You could do it with other things as well, but those are our primary applications for bearings. Example 6. A ship leaves port heading north 20 degrees east and sails 9 miles. Then the ship turns and heads south 70 degrees east and sails for 5 miles. Question A. How far is the ship from the port? And question B. At what heading could the ship have set sail in the beginning to sail directly to its end position? All right, so let's draw a grid here. And we'll mark this origin as the port. That's the port where the ship set sail from. The ship is going to go north 20 degrees east. So we're going to go out 20 degrees here, like that, and go up 9 miles. We just need to note that that's 9 miles. And for the angle, I'll draw that in green, that's 20 degrees. At this point, the ship then turns and heads in a direction of south 70 degrees east. All right, to do that, I need to get a new coordinate system drawn. And so we re-coordinatize the grid as sort of having a new original point, a new point to begin this trick. And we do that so that we can draw south 70 east. So south 70 east is going to open this up 70 degrees from south going toward the east, and it's going to come out like this. So let me draw that in blue, and it's only 5. That may be too much. It's only 5 miles, so I'll draw it smaller. But the angle was 70 degrees there. But that angle only goes to the new coordinate system. And then the question is, how far is the ship from the port? So we want this new distance that I've drawn in purple. And once you get this general picture down, it's a lot easier to take this and translate it into a free diagram. So in the free diagram, you just use the pieces of the triangle. So here's our 9. We need to realize something about this triangle right away. We had an angle of 70 degrees here. Using some old-fashioned geometry, since the coordinate grids are parallel, the angle between the triangle side and the new coordinate side, that is south, is actually 20 degrees as well. And so that makes this angle a right angle. So we're going to go out 5 miles, but this is a right angle. You may need to convince yourself of that. Question 8, how far is the ship from the port? Well, the distance from the port to where the ship is now, we'll just call x, and that turns out to be the hypotenuse of this triangle. So x squared is equal to 9 squared plus 5 squared, and we get x is equal to 10.30 miles. And the second question is, at what heading could the ship have set sail from the beginning to sail directly to this endpoint? On our free diagram, let's call this angle theta and solve for theta. So we can use the tangent relation. So tangent of theta is equal to the opposite, 5, divided by the adjacent, 9. And taking the arctangent, we would get theta is equal to 29.05 degrees. Now that is not the answer. That is theta in the original picture, which is this angle here inside the triangle. The actual heading that we need to draw is the one that goes from the north axis all the way over to the side of the triangle. That's the purple side. And so we need to take this theta and add the original 20 degrees to come up with 49.05 degrees. And then let's write that as a bearing. So it's north 49.05 degrees east.